let's talk about parabolas. We're going to be able to derive the equation of a parabola given the focus in the directrix. You're going to learn all about how parabolas really are built from the ground up. So the parabola is a set of points that are of equal distance from two things, a point called the focus and a line called the directrix. So let's set that up. Let's have a point with the coordinates a comma b, x coordinate a, y coordinate b. We're going to call that the focus. And then let's have a line here. You can see that represented that with the purple line. Coordinates y equals k, it's a horizontal line. And we're going to call that the directrix, the building blocks of the parabola. So let's start by creating our first point on the parabola. And that would be, if it's equally distanced from the focus and the directrix, we're going to probably put that first point right here, because it's 2 spaces away from the directrix and 2 spaces away from the focus. Equal distance. So next we're going to find another point here, let's say to the left of A, that is an equal distance between the focus and the directrix. And clearly I don't have it right here, so we're going to have to move that point B around until I get the exact same distance for both of them. Now remember, by distance we're talking about we have to be perpendicular to the directrix, because the shortest distance between a point and a line is always through the perpendicular, if you remember from geometry. So here I found that point. It's exactly 2.24 away from both the focus and the directrix. And again, it's got to be perpendicular here because that's the shortest distance. That's how we measure it. And we can reflect that across the axis that goes through the focus and the directrix over to this point C that is also equally distant from the focus and the directrix. In a similar way, we can create additional points here at point D and point F that are also the same distance away from the focus and the directrix, again remembering to be perpendicular with the line. And we can continue this process, and you can already see the shape of a parabola developing here. And if we continue this process with even more points, we'd have a nice parabola. And in fact, if we drew that parabola, this is what it would look like. So again, the parabola is a set of all points that are the same distance from a point called the focus and the directrix. And if you notice, that very first point, that point that was halfway between the focus and the directrix and kind of the closest distance it could be from both of them is, you remember that term from algebra, the vertex. So let's go ahead and pick a point arbitrarily on the parabola, and it's going to have the coordinates x comma y. And since the definition of a parabola is it's the set of points, or the locus of points, with the same distance between the focus in the point and the directrix in the point, we're going to have to find both of these distances algebraically. Well, we know from the distance formula, the distance here between a comma b and x comma y is going to be the square root of y minus b squared plus x minus a squared. And that comes straight from the Pythagorean theorem. So that's D1. Now if we look up here at D2, it's the difference between x comma y and x comma k. And since the x coordinates are always going to be the same, because we're going perpendicular here, it's the y coordinates that are the difference. So it's going to be y minus k. And that really is the square root of y minus k squared, because the difference in the x's is 0. So that distance also comes from the Pythagorean theorem. We're going to set them equal to each other because that's the definition of a parabola, where D1 equals D2. And to make things easier for us, we're going to go ahead and rewrite D2 in a similar fashion to the way we wrote D1. So they look like each other, and notice this really doesn't change anything. We're just kind of rewriting it in terms of the Pythagorean theorem. So we're going to set D1 equal to D2. And when we do that, this is what we get. So that first distance between the focus and the parabola is the same as the distance from the parabola and the directrix. So when we square both sides, this is what we get. The focus to the parabola distance equals the directrix to the parabola distance. Now let's go ahead and move the y terms over to one side. And once we do that, we have the x terms on the left side and the y terms on the right side. And what we're going to do is go ahead and expand both of these binomials on the right-hand side. After that binomial expansion, and never forget about those middle terms in binomial expansions. That's the most common mistake, by the way. So after the binomial expansion, this is what we have. And notice, looks like we might be able to get rid of some terms, and in fact, we can definitely do that. We can get rid of the y squareds because they're going to cancel each other out, which leaves us with a somewhat simpler situation here. Now we're going to take this negative sign and distribute it out to both of the terms on the right, and this is what we're left with on the right-hand side. So let's now group some of these terms together, the negative 2yk and the 2yb, and then move the constants, the k and the b, over to the right. And then we're going to kind of factor by grouping, because you can see there's a commonality here in these first two terms. They both have a 2 and a y in them. In fact, I'm going to take a negative 2y out of both terms, so notice that kind of changes the sign here. I can rewrite these as negative 2y times the quantity b minus k, and put a minus sign in front of these terms, basically factoring out a negative 1, and then it becomes, instead of plus k squared minus b squared, I'm going to rearrange the terms and I get negative b squared minus k squared. So we're factoring out a negative 1 out of both those terms. What is here is the same as what is here. And the reason for doing that is to, again, we're going to factor by grouping. So what we can see here is that b squared minus k squared is the only binomial expansion that doesn't have a middle term. It factors, if you recall from Algebra 1, it factors into b plus k times b minus k. And notice there's a b minus k here, there's a b minus k there. So now we can factor by grouping. Now we're going to try and divide by a common term. And the common term includes a b minus k. We're going to divide both sides by b minus k, but we're also going to divide them by 2. So we're going to divide it by 2 times the quantity b minus k. And the 2 isn't exactly obvious, but we're going to do it anyway. And when you do that, this is what you have. Okay, now when you simplify this and divide out the 2 times b minus k out of all the terms in the numerator on the right-hand side, an interesting thing occurs, and what you get is, on the right-hand side, y for the first part minus the quantity b plus k over 2, which is very close to what we call the general form of a parabola. Remembering that b and k are constants, so what we have is 1 over 2 times the quantity b minus k, which is a constant, by the way, times x minus a squared equals, on the right-hand side, y minus the quantity b plus k over 2. This term is also a constant. So let's take what we've derived, this very complex function, and apply it to the parent parabola to help find the focus and the directrix of that parabola. And that parent parabola is y equals x squared. It is the parent of all parabolas. So how do we relate this to y equals x squared? Well, let's look at things that they have in common. There's the y. There's the x squared part, and so if x squared has to fit this x minus a squared, that must mean, first, that a equals 0. Secondly, this b plus k over term must also equal 0. And finally, this coefficient on the x minus a squared has to equal 1 if this thing's going to match y equals x squared. So 1 over 2, the quantity b minus k, has got to equal 1. So for our parent parabola y equals x squared, to match this equation that we've derived for all parabolas, these things must be true. A equals 0, b plus k over 2 equals 0, and 1 over 2 times b minus k must equal 1. And since the focus is at the point a comma b, and the directrix lies along the line y equals k, if we solve for a, b, and k, we actually find the focus and the directrix for the parabola. Well, the a equals 0 part's done. We're going to take these two equations and solve for b and k. 2 equations, 2 variables, we can do this. We take this first equation and multiply both sides by 2, we get b plus k equals 0 times 2, or 0. If we take this bottom equation and multiply both sides by b minus k, we get b minus k equals 1/2. 2 equations, 2 variables, they're both linear. If we add both equations to each other to solve for b, we're going to get that 2b, b plus b, the k's cancel out, equals 1/2. So 2b equals 1/2, so, and b equals 1/4. So we have the coordinates of our focus. Since we know a and b now, we know the focus is at the point a comma b, or in this case, 0 comma 1/4. The focus is at the point 0 comma 1/4. And if we substitute this value of 1/4 in here, into b plus k equals 0, or the bottom equation, you're going to get that k must equal negative 1/4. So now that we know k, we know the equation of the directrix. The directrix is at y equals negative 1/4, which kind of makes sense. If you look at the y equals x squared parabola, all the points are going to be equally distant from that point 0, 1/4, and the directrix, the line, the purple line here, y equals negative 1/4. So generally, for all parabolas, not just y equals x squared, this formula holds, and the information we need, or the information we will get, is that the focus is always at the coordinates a comma b, and the directrix is at the equation y equals k. So the critical variables here are a and b and k, which determine the shape, size of the parabola, because they determine where the focus and directrix are. So let's take this and apply it to any parabola, and we'll take that formula that we've derived for the equation of all points that are equally distant from a focus and a directrix, and match it up with a more common version of the parabola, which is called its vertex form, where x1 comma y1 represent the coordinates of the vertex. Looking at these two equations that we've developed, y1 appears to match this term right here, b plus k over 2, perfectly. x1 appears to match a perfectly. And then we're going to call this thing capital A, which represents the coefficient in front of the x minus a squared term. So putting it all together, x1 is equal to a, y1 is equal to b plus k over 2, and this coefficient term a, which we'll call capital A, different from little a, is equal to 1 over 2 times b minus k. We know these three things must be true if the coordinates of the vertex are x1 and y1. Now if we solve for both of these, like we did in the y equals x squared example, for b and k, we take these two equations here and solve for b and k. So if we multiply both sides of the first equation by 2, we get this equation, 2y1 equals b plus k. And if we multiply both sides of this equation by b minus k and then divide by 2, we get 1 over 2a equals b minus k. Add both equations together, and you're going to get that 2b equals this plus this. And then you can see there's a 2 everywhere, so divide everything by 2 to solve for b. And you get the idea that b equals y1 plus 1 over 4 times the quantity that's before the x minus a squared, the coefficient. Substitute that value of b into the other equations for k, and you're going to get that k is y1 minus 1 over 4 times that coefficient again, which is an interesting pattern, and hopefully it's going to make sense when you put it on the parabola itself. If we take that b, which by the way is the y-coordinate of the focus, it's going to be equal to the y-coordinate of the vertex, y1, plus some distance, which is 1 over 4 times the coefficient on the x side. If we take this k term, which by the way is the directrix's y-coordinate, it's going to be the y-coordinate of the vertex, y1, minus that same distance, 1 over 4 times the coefficient. Now remember, the coefficient's in the denominator in both cases. So we either add that distance or subtract that distance from the y-coordinate of the vertex. So let's look at an example. Equation y minus 4 equals 1/2 times x minus 2, the quantity squared. That's a parabola in vertex form. Well, we know that the coordinates of the vertex are going to be whatever makes x 0 and whatever makes this y part 0. And that's the point 2 comma 4, because 2 makes that 0, 4 makes that 0. Remember, if there were positive numbers here, you'd wind up with negative coordinates, because again, it's what makes that what's in parentheses 0. So we know the vertex of this thing is going to be at the point 2 comma 4. So the next question is, where's that focus and where's that directrix? Well, we know the focus is at the point a comma b, and we know the x-coordinate is the same, so it's 2. But what's the y-coordinate? Well, the y-coordinate of the focus is given by b equals the y1, the y-coordinate of the vertex, plus that extra term, 1 over 4 times a. In this case, since that a term, that coefficient term is a 1/2, this becomes 4 plus 1 over 4 times 1/2, which is equal to 4.5. So now I know my focus is at the point 2 comma 4.5. I've gone up to get to the focus, from the vertex to the focus, I've gone up a distance of 0.5. The directrix is on the equation y equals k, and it lies below the vertex the same distance as the focus. And we know that distance is 0.5, so it's just 4 minus 1 over 4 times a half, or 3.5. So now we know everything we need to know about this parabola, chiefly that its vertex is at 2, 4, x1, y1. Its focus is a distance above that at 2, 4.5. That distance is 1 over 4 times the coefficient. And its directrix is the same distance below it. It's at 4 minus 1/2, or 3.5. And all the points on that parabola have to be the same distance from that focus and directrix. So that's the parabola, the set of all points that's equal distance from a focus and a directrix. You've derived it. You now know how to use it and translate between the forms of the parabola.